Hi guys, it's Mrs. Jackson. Today's video lesson is going to be calculating pH at varying points during a weak acid strong base titration. Keep in mind the experiences you've had in the laboratory and try and place these calculations at different points during the titration labs that you've completed. For our titration examples today in our burette, we would have sodium hydroxide, concentration 0.4 molar. And the acid that we have in our flask is a 0.2 molar solution of methanoic acid. So kind of keep those in mind. Okay. Before we get started on the calculations, be sure that you've got your square of fun out. I would recommend having your IB data booklet. You're going to need your notes so you can get down these examples, your calculator, and of course your thinking cap. A couple of things that I want you to remember as we get started. We've discussed this multiple times, but today, since we are looking at a weak acid strong base titration, when we hit the equivalence point, when the moles of acid equal the moles of base, our pH should be greater than 7. We're going to talk about why that is as we get to the calculation, but do keep in mind that's where the pH should be at the equivalence point. A couple of other things to keep in mind are those equations that we use quite frequently to make some of our calculations. Need to remember the Ka or the Kb expression is always the concentration of product ions over the reactant ions. Molarity equation is moles of solute per liter of solution. We use this equation quite a lot to calculate moles for our various equations in today's example. The pH formula. pH is the negative log of the hydrogen ion concentrations. Also be sure that you've got your square of fun so you can work backwards to pH from pOH as we get into some of these concentrations or calculations. And then down here at the bottom is one that we've worked with in class but is new to the videos, and this is the Henderson-Hasselbalch equation down here at the bottom, where the pH of a buffering solution is equal to the pKa of the acid plus the log of the conjugate base ion concentration over the concentration of the weak acid. I've got these equations appearing on future slides, but I do want you to be thinking about these, and I think you should get those down in your notes before you move forward. So, what we're looking at today with our set of practice problems, and this was handed out in hard copy form in class on a yellow sheet, I believe, is we're simply calculating pH during a titration. We have 50 milliliters of our methanoic acid, concentration 0.2, and to that acid sample, we will be adding different volumes of a 0.4 molar sodium hydroxide solution. Okay, so you can see the problems that we're going to solve. We've got the initial concentration on letter A, and then we're going to be adding amounts of sodium hydroxide and making calculations at each of these points of a titration. A few pieces down here at the bottom I've already gone ahead and worked out for you. We are going to be needing the moles of acid on a couple of slides here as we get going. I've gone ahead and calculated the moles of acid that we have for the methanoic acid by plugging in the molarity of the acid, 0.2, and the volume of the acid, which is 50 milliliters. When you use this equation, you have to convert those 50 milliliters to liters. So I've taken the 0.2 molarity times 0.05. So I have my 0.2 molarity. And then in the volume, I subbed in 0.05 liters. And that is how I came up with the 1 times 10 to the negative 2 moles of methanoic acid. So when you see this pop up in a couple of slides, this is where that came from. The other thing that we have done, the pKa for methanoic acid from the data booklet is 3.75. If you don't remember, this is a good review, that to go from the Ka value to the peak, or from the pKa value to the Ka value, you take 10 to the power of negative pKa. When I did that, my Ka value calculates down here at the bottom to be 1.78 times 10 to the negative 4th. We're going to need these values for several slides as we get going. So be sure you have those written down and that you understand where those values have been calculated. So let's get going. Let's do this. All right, so for our first part of the problem, we have just our methanoic acid by itself. I've got 50 milliliters of my 0.2 molar methanoic acid, and I have added 0 of my sodium hydroxide. So really, for this initial concentration or for the initial pH, all I have is the dissociation of my methanoic acid. I have my 0.2 is the molar concentration I have of my methanoic acid, and because this is an ice chart, I am using molarities. Molarities are always used in our ice charts. But because this reaction is just getting started, I have 0 hydrogen and I have 0 of the conjugate base anion when I start, or before the acid dissociates. So remember, that's going to pull the acid forward, and as it moves forward to fill in those zeros, I know I'm going to lose some amount of my 0.2 molar. So when I fill in my chart, I know I'm going to lose some amount of my methanoic acid, and I remember that I'm going to gain that same X amount of both the hydrogen ion and my methanoate conjugate base anion. So when I reach equilibrium, when this finally balances out, I've got 0.2 minus X. That's what I have left of my weak acid. And at equilibrium, I have formed X amount of hydrogen ions, and I have formed X amount of the methanoate conjugate base anion right here at the top. Remember from earlier lessons that we have discussed that because this has such a small Ka, 1.78 times 10 to the negative fourth, I know that this X, by comparison to the 0.2, is going to be very, very small. So we say that that X is negligible and we ignore it. And keep in mind, there is a 5% rule that we have discussed previously. When the calculation is over, we would normally take that X and compare it to the 0.2. We would divide X by 0.2, and as long as it's under 5%, we were correct to ignore it. For all of our calculations, the X will be negligible. So to solve this equation, right, or to solve for X, I've got to come back up here and I'm going to utilize my Ka expression, where the Ka of my acid is equal to the concentration of our anion times the hydrogens over the acid concentration. Notice that the Ka expression is written for ethanoic acid. We are using methanoic acid, but the Ka expression looks the same. So I fill in my Ka value, 1.78 times 10 to the negative fourth is equal to, and I'm just going to put my X squared at the top because my hydrogen concentration is one of the X's, and then the conjugate base is the other of the X's, and so that's X squared. And I put that over the initial concentration of my acid, which was 0.2 molar. Plugging that into my calculator, I find that the value of X is 5.97 times 10 to the negative third. When I take the negative log of that to get my pH, I find that the value of my pH for my initial solution is 2.22. So that's the concentration of my weak acid times the Ka of my weak acid. Square root that value to get the value of X, which is 5.97 times 10 to the negative third. And then I take the negative log of this value to get my pH of 2.22. All right, moving on to the next slide. For this slide, we're doing something different. Instead of having just the acid in my flask, now I'm going to add 5 milliliters of base. So I've got a chemical reaction happening in this before I can calculate the pH of my solution. I have an acid. To that, I'm adding a strong base, and that's going to be a neutralization reaction. Anytime we look at chemical reactions, we have to be working in the mole units. Okay? So to find the moles for my acid, I took the 0.2 molar, just as we discussed in the first slide. I put 0.2 molar in for the concentration of my acid. For the volume of my acid, I plugged in 0.05 liters, and that multiplied to give me 1 times 10 to the negative 2 moles of acid. I did the same thing to find the moles of base. Using the same equation at the bottom, my base is molarity 0.4. The volume for this addition is 5 milliliters. Converting that to liters, 0.005. So I have 0.005 liters times 0.4 molar sodium hydroxide to give the 2 times 10 to the negative 3rd moles of base. Now that I'm looking at these, this is a chemical reaction. When I start, I haven't any of the sodium methanoate present. Okay? And I know that I'm going to use up some of my reactants to form products. Well, this is a 1-to-1 molar ratio. For every 1 molar of methanoic acid I use, I'm going to use up 1 mole of sodium hydroxide. So the ratio is 1-to-1. Looking at these values, the sodium hydroxide is smaller, and so the sodium hydroxide in this step of the process is going to be my limiting reactant, which means it's going to be entirely used up. Okay, so I'm going to use all of the sodium hydroxide, so I'm going to lose 2 times 10 to the negative 3rd moles. And I'm going to have no sodium hydroxide when I'm finished. And I'm going to use up the same amount of my acid because it is a 1-to-1 ratio. So when I'm finished, after the reaction is completed, I'm going to have 8.0 times 10 to the negative 3rd moles of my acid left over. And I'm going to form 2.0 times 10 to the negative 3rd moles of my anion. This is essentially my X from the previous example. I know I'm losing this amount of my sodium hydroxide, and I'm going to form exactly the same amount of that salt. I used up the same amount of the acid, subtracted it to give me 8 times 10 to the negative 3rd. I will finish the reaction with 2 times 10 to the negative 3rd moles of my salt. Okay. I'm still going to I need to find my pH of my solution. In order to do that, normally we would put this into an ice chart. And if we're going to calculate from an ice chart, we need concentrations. Because these are only moles, I need to convert those into concentrations using the same equation down here. Molarity, which is what we need, is moles of solute over liters of solution. So the 8 times 10 to the negative 3rd are my moles. I need to divide that by the liters of solution. Well, I now have a new volume for my solution. I had 50 milliliters of acid, and I added to that 5 milliliters of sodium hydroxide. So my new volume is 55 milliliters. So I'm going to divide my moles by 0.055 liters to get my new concentration. For these methanoic acid, that's going to be 0.145 molar. I'm going to do the same for my methanoate ion. Remember, sodium is a spectator, so we don't really worry about him. So I take 2 times 10 to the negative 3rd moles of my anion and divide it by the same volume, 0.055 liters. And that concentration calculates to be 0.0364 molar concentration of the methanoate ions. Now that I have molarities, I can start to calculate concentrations. Instead of using an ice chart, though, we're going to use the Henderson-Hasselbalch equation. So for some of you, it may be a review. For some, it may be the first time you've seen it. From the bra chart that we just utilized, okay, so from our bra chart down here at the bottom, we calculated our new molarities. The new molarity for my methanoic acid was 0.145. The concentration of my anion was 0.0364. and I'm going to plug those into the Henderson-Hasselbalch equation. So I'm going to plug in my values into the Henderson-Hasselbalch equation. Let me move this down just a hair. So we're going to take our pH. Our pH is equal to the pKa plus the log of the conjugate base over the acid. So for our calculation, pH is going to be the pKa of my acid, 3.75, plus the log of, I've got my anion, 0.0364 molarity, over the acid concentration of 0.145. When I plug that into my calculator, I get a new pH value of 3.14. You could take these two concentrations here, and you could put those into an ice chart, into the initial line of an ice chart, and still go through and minus X and plus X. It will lead you to the very same calculated answer of 3.14. Alrighty, moving on to the next calculation. So similar to the one that we just completed, I still have 50 milliliters of a 0.2 molar solution of methanoic acid. My concentration of sodium hydroxide is still 0.4, but now I'm adding 12.5 milliliters. Okay, so I have calculated the moles using my molarity equation. So for the acid, I had my molarity of 0.2 was equal to X number of moles over the volume of solution, 0.05, and that is how I calculated 1 times 10 to the negative 2 moles of acid, just like on the last one. For the base, I did the exact same thing with the base values. I took my base molarity of 0.4, and I calculated using 12.5 milliliters, so 0.0125. When I multiplied those to get X, I find that that is 5 times 10 to the negative third moles of the base. So just like in the previous example, I know I'm going to lose X amount of one of these. When I look at the values, I've got 1 times 10 to the negative 2 and 5 times 10 to the negative third. This is a smaller amount, so it's going to be used up. That means in this example, sodium hydroxide is again our limiting reactant, so it's going to be used up entirely. So I'm going to lose all 5 times 10 to the negative third moles of my sodium hydroxide, and I'm going to lose an equal amount of the base. So of the 1 times 10 to the negative 2 moles I start with, I'm losing 5 times 10 to the negative third moles of that. And I'm going to form 5.0 times 10 to the negative third moles of my conjugate base, my HCOO minus. Again, ignoring sodium, it is a spectator. So when the reaction is over, the sodium hydroxide is gone. 1 times 10 to the negative 2 minus 5 times 10 to the negative 3 is 5 times 10 to the negative 3. And then I form 5 times 10 to the negative third moles of my conjugate base. So you may notice that these two values are the same, and this is a very, very important point. Okay, I'm going to go ahead and walk you through a couple of pieces and calculations, and then I'm going to explain to you how important this point is. All right, so I want concentration again because I need to calculate my pH. In order to get concentration, I have to use this equation. Molarity is equal to moles over liters. These are my moles of acid. These are my moles of base. So to find the concentration, I have to divide by the volume of solution. So I had 50 milliliters of acid, and I added 12.5 milliliters of base, which gives me a value of 62.5 milliliters. So I will divide my moles of acid, 5.0 times 10 to the negative third moles of acid, divided by 0.0625 liters of solution. And I'm going to do it for each of these values, 0.0625 liters. Both of those are going to calculate the same. The molarity of each of those solutions is going to be 0.08 molar. You can plug that into an ice chart. Okay? You can plug it into Henderson-Hasselbalch, but we have reached the half equivalence point. Half equivalence is when you've used up half of your moles of acid or base. When I look at this point in our titration, I have used up half of the acid I had. I have formed equal amounts of conjugate base. So anytime that you have the same number of moles of your weak species and its conjugate, you are at the half equivalence point, and that is the ideal buffer because that's the maximum of both species that you could have. All right, so the half equivalence is when the moles of the strong use up half of the moles of the weak. So that is where pH is going to equal pKa. So because pKa is 3.75, I know that my pH is also 3.75. You could, if you wanted to, plug this into Henderson-Hasselbalch and you would wind up with the same thing. I don't think I can move my writing. Rewrite it. Okay. So if you plug it into Henderson-Hasselbalch, sometimes people don't remember the value of that half equivalence point, and so they just continue to plug numbers into equations. You have 0.08 molar concentration of your acid, you have 0.08 molar concentration of the anion. So if you plug it into the equation, your pH is equal to pKa of 3.75 plus the log of 0.08 over 0.08. Well, 0.08 divided by 0.08 is a 1, and the log of 1 is 0, so your pH equals 3.75. So that's nice to know at your half equivalence. You can show the math to justify choosing the pKa value, or you can explain it with words. All right, calculating another value, we've got the same solution of methanoic acid, so we're starting the same number of moles, 1 times 10 to the negative 2. This time I have increased the volume of sodium hydroxide that I'm adding to 24.5 milliliters of sodium hydroxide. Calculating the moles of base, okay, that is 9.8 times 10 to the negative third. What I did was I subbed in my molarity of base, 0.4, is equal to X number of moles over the volume of base, 0.0245, and that X value calculates to be this 9.8 times 10 to the negative third. So now, same as we've looked at before, because this value is smaller, the sodium hydroxide is still going to be my limiting reactant. So I'm going to use up all of the sodium hydroxide. I'm going to use up 9.8 times 10 to the negative third moles of sodium hydroxide, and I use up an equal amount of the base, of my weak acid. Okay, and I'm forming that same amount of my conjugate base on the right-hand side. So when the reaction is over, the base is completely gone. I have formed 9.8 times 10 to the negative third moles of the conjugate base, and I only have 2.0 times 10 to the negative fourth moles of my weak acid left over, which isn't really very many, right? We've really used up almost all of it. I still want to find my pH, and pH is based on hydrogen concentrations. So I'm going to divide by solution volume. I had 50 milliliters of my acid. I added 24.5 milliliters of sodium hydroxide. My new total volume is 74.5. As liters, that is 0.745 liters for both solution, or for both concentrations. I use the same volume. My weak acid concentration is going to calculate to be 2.68 times 10 to the negative third. And my conjugate base concentration is going to be 0.132 is my concentration. You could plug those into an ice chart again, or you can plug them into Henderson-Hasselbalch. So from the other slide, my weak acid concentration has decreased and is only 2.68 times 10 to the negative third. My anion concentration was 0.132. Plugging those into Henderson-Hasselbalch, my pH is equal to 3.75, which is my pKa, plus the log of 0.132 divided by 2.68 times 10 to the negative third. When you calculate that out, the pH for this solution has risen to a 5.44. Henderson-Hasselbalch is a tremendous time saver, but ladies and gentlemen, I want to point out that it only works if you have both the concentration of the conjugate base and of your original weak acid. We didn't use this on our first calculation today because the concentration of the conjugate base was X. Okay. So I couldn't use that for my initial pH. You can only use it for a buffering solution where you have concentrations of both the weak acid or base and of its conjugate species. But it is a time saver. All right, moving on to the next sample calculation. When I look at this calculation, again, I have plugged in my moles. And so I have the same 1 times 10 to the negative 2 moles of my methanoic acid. But when I calculate the moles for my base using 0.4 molarity and 25 milliliters, my moles calculate to be 1 times 10 to the negative 2. So hopefully you recognize that we have arrived someplace very important, and that is the equivalence point. So this is going to be a very important calculation because we have just arrived at the equivalence point. Remember, that's when the moles of our weak acid are equal to the moles of base, or moles of any acid is equal to the moles of any base. So this is going to be my equivalence point, which means both of the acid and the base will be used up because they have the same amount. I use up 1 times 10 to the negative 2 moles of both. And I form 1 times 10 to the negative 2 moles of my conjugate base. So after the reaction is over, acid is gone, the base is gone, and I have 1 times 10 to the negative 2 moles of my conjugate base remaining. So this is an important part of our equation. There are a lot of pieces to this particular calculation, so pay close attention and go back and review it if you need to. But at this point of my reaction, all I have in solution is the 1 times 10 to the negative second moles of my conjugate base. I still need to find a pH, which means I'm still going to need a concentration. So I'm going to divide my mole value of 1 times 10 to the negative 2 by the total solution volume, which is 75 milliliters, the 50 mils of acid plus 25 of the hydroxide, and that is 0.075 liters. So when I calculate that value, the concentration of my conjugate base, my HCOO minus, is going to be 0.133 repeating molarity. And that's the only thing that I have in solution. So that flips a few things on its head. So let's kind of take a look at this. First of all, this is a conjugate base, all right? So I no longer have the same dissociation I had. So this is my equivalence point when you were doing your graphs. It kind of looked like this. So you've got that funny little start where we had a low pH, and then we kind of got to our 3, and then we start to kind of level off. My pH at equivalence should be above 7. So we're going to see if that holds true. So to do this, I have to come up with a new equation. Because I don't have the weak acid, all I have left is my conjugate base. I had to come up with a new dissociation equation. Okay. So my dissociation equation, this is the weak base anion. It's all that was in solution. And it cannot stay an anion. If you remember, we had at the very beginning, we had a Ka value for our acid, okay, of 1.78 times 10 to the negative 4th Ka value. Well, that Ka value with that negative exponent tells me that the reactants are favored. And the reactants from our first equation, okay, our first dissociation equation, were our weak acid, okay, breaking into the hydrogen ions and into the anions. Okay? And that negative exponent that you have right here, okay, tells me that the weak acid was favored. This is our anion here. It is not favored in solution. So what happens when you have only this conjugate base in solution, it is desperately trying to get back to that weak acid. This formation of this anion is not favored in solution, so it's trying to get back to its acid form with the hydrogen in front. Well, when you're in a water solution, the only place to get a hydrogen is from a water molecule. So what we find has happened is that this conjugate base right here, this anion, in an attempt to get back to that weak acid form, will take a hydrogen from the water to form its original weak acid. Okay? And when the hydrogen is removed from the water, that leaves the hydroxide in solution instead. Oops. So what we find is that this anion removes the hydrogen from water to reform that little bit more stable weak acid, and when it does so, it leaves that hydroxide, and the hydroxide formed here is the reason that your pH here is above 7. It has nothing to do with the strong base, except for the fact the base is what we use to react and get rid of our weak acid. So this is as hard as it gets right here, this step, remembering to take that anion, react it with water to form the weak acid and hydroxides. So now that we have our new dissociation for the conjugate base, what we're going to need to do is calculate the pH. Well, this is going to be another ice chart because I have 0 weak acid when I start and I don't have any hydroxide. The concentration of the weak base that I have from the previous slide is 0.133 repeating. So that's my concentration. I know that this is going to decrease by some amount that's X, and I know this is going to increase both the weak acid concentration and my hydroxide concentration by that same amount x. So at equilibrium, I'm going to have 0.133 minus x, and I'm going to have x amount of methanoic acid, and I'm going to have x amount of my hydroxides present. Okay, a few more pieces we have to put into place. So when I look at this equation, okay, when I am looking at my dissociation, this is a conjugate base, but this is a Ka value. In order to do anything with my ice chart, I can't use a Ka, dissociation for an acid constant, for a base. But the Ka of my acid is related to the conjugate base. Down here at the bottom, a couple of things you can do. Okay. Two ways you can look at this. Okay. The Ka of your weak acid times the Kb of its conjugate base is equal to Kw, which is 1 times 10 to the negative 14th. That's your ionization constant for water. The other way you could look at it is similar to pH, where pKa, you can look at it this way, where pKa of your weak acid plus the pKb of its conjugate base is equal to 14, just like pH plus pOH is equal to 14. I'm going to use this equation, okay, to find my pKb and then find my Kb. So what I'm going to do, okay, my pKa was 3.75, so 14 minus 3.75 is going to give me my pKb, which is going to be 10.25. That's my pKb. And if I want the Kb value is 10 to the power of negative pKb, which is negative 10.25. So in this case, my Kb value is going to calculate to be, wait for it, my new Kb value for this problem that we're going to solve is going to be 5.62 times 10 to the negative 11th. Okay. So pause it, work through that, play it again if you need to. I'm going to erase this because I need the space. Okay. So now that I have my new Kb value, now I'm ready to plug in my values into my Kb expression. Remember, your Kb expression is going to be just like a Ka expression, only I've got the hydroxides. This is going to be my weak acid, and this is my conjugate base down here. So I'm going to plug in my Kb value, 5.62 times 10 to the negative 11th is equal to x squared over 0.133 repeating. When I calculate that, my value of x, which you have to remember in this case is hydroxide, calculates to be 2.73 times 10 to the negative 6th. If I take the negative log of that, my pOH calculates to be 5.56. And if I subtract 5.56 from 14, my pH calculates to be 8.44. And on our previous slide, we said that the pH at the equivalence point should be above 7. In class, we've talked about it's usually somewhere between 8 and 9. And when I look at my calculated value of 8.44, I see that that is all true. Okay. The steps that you have to follow at the equivalence point are the hardest that they're ever going to be. Okay, it's the one and only time that you have to flip this equation. It's the only time that you've got to find the KB. Okay, it's the only time you have to do all this work, is the equivalence point only. Okay? So go back and watch the equations or the explanation for the steps on part E as many times as you need to understand what we're doing. We have 2 calculations left to do with our weak acid strong base titration. So in this case, I continue to use that same 1 × 10⁻²⁰ moles. I am adding 25.5 milliliters of sodium hydroxide, okay, which calculates to be 1.02 × 10⁻² moles. In this case, the weak acid is going to be my limiting reactant. So on this part of the problem, I'm going to use up 1 × 10⁻² moles of the acid, and I use up the same amount of the base, 1.0 × 10⁻². We do form 1.0 × 10⁻² moles of the methanoate ion. Remember, we don't worry about sodium. But it's not going to matter a whole lot. Let me show you why. So after the reaction's completed, the acid that we started with is completely gone, and I have lost 1 × 10⁻² of the sodium hydroxide. That's going to leave me with 2.0 × 10⁻⁴ moles of my sodium hydroxide left, and I do form 1 × 10⁻² moles of my conjugate base. But because we have sodium hydroxide left over, and because it is a strong base, it is going to so completely dominate the solution that the amount of conjugate base that we formed is negligible. Okay? Because your conjugate base, HCOO-, had a pKb of 5.62 × 10⁻11. This is going to be a negligible value, and so we do not worry about this. We simply look at the sodium hydroxide. I've got 2 × 10⁻⁴ moles. I need to find a concentration to find pH, so I divide it by total solution volume. So I have those 50 milliliters of acid plus the 25.5 milliliters of base, and that is 0.0755 liters, which gives me a molarity of sodium hydroxide equal to 2.65 times 10, goodness sakes, times 10⁻³ molarity for my sodium hydroxide. I take the negative log of that to get my pOH. Okay, pOH is 5.56. pOH calculated as 5.56. When I subtract that from 14 to get the pH value here is 11.42. Okay. Moving on to the final calculation is going to be just the same as the last. Okay. I'm going to have the weak acid is now my limiting reactant. I'm going to use up all 1 × 10⁻² moles of my weak acid. I use up an equal amount of the base, and I do form 1 × 10⁻² moles of the conjugate. After the reaction is over, there is no weak acid remaining. And when I subtract that 1.0 × 10⁻² from the original number of moles, after the reaction is over, I have 6.0 × 10⁻³ moles of base remaining, and I have that 1 times 10 to the negative 2 moles of the conjugate anion that we've formed. Again, because this is a strong base, it's going to dominate this solution. The pKb, or I'm sorry, the Kb value of our conjugate base here was so very small that this is going to have a negligible effect on the solution pH. So we simply need the concentration of sodium hydroxide. I take 6.0 times 10 to the negative third. I divide it by total solution volume, which in this case is the 50 milliliters of acid plus the 40 milliliters of base. So that's 90 mils, so 0.09 liters. And that gives me a sodium hydroxide concentration of 6.67 times 10 to the negative second molarity. Taking the negative log of that value, I get a pOH value of 1.18. When I subtract that from 14 to get the pH value, it is a 12.82. And there you have it. That is how you make pH calculations at varying points during a titration. Please watch this video as many times as you need to. If you have questions, please write those down and bring those to class, and I'll be happy to help you with those. So, until I see you in class, bye-bye.